Hi and welcome. So today we're going to be asking the fundamental question about what is matter. And we're going to be taking a broad approach. We're going to be looking at the physical states of matter. We're going to be looking at substances within matter, so how homogeneous or heterogeneous the matter is. And then we're going to be delving in to looking at things at an atomic level and seeing that matter really is composed of small particles that we're going to identify as atoms. So as we begin our discussion talking about what is matter, let's consider the following. Let's say that you and your friend are out and about hiking. You can see here from this picture, this is a lovely day just to the west of Silverton. Silverton, Colorado is about right there in the distance, and we have the Ice Lakes Basin right here. I think this is Golden Horn, 13,000-foot peak. And as you're standing atop this peak, you're taking in the vista, you're looking at the mountains and the leaves and the foliage, and perhaps even looking at the oncoming clouds, and all of this is matter. And so perhaps you're having a thought to yourself, what does all of this compose of? So what is matter? And this is a good question, and this is something that we're going to try and figure out today. As chemists, we like to classify things. We like to think about breaking things down into their components and being able to look at those components and identify them. And so we can classify matter, the stuff that we see around us, everything that we see, breathe, touch, feel, hear. We can classify it in a whole bunch of different ways. And one of the ways we can do this is we can classify it by its physical state. So we all know that given an object, given matter, that it can exist in a variety of states. So we have we can think about things as solids, we can think about things as liquids, and we can think about things as gases. There actually are other states of matter, such as plasmas, but they only occur in things like aurora borealises and on the surface of the sun. So on Earth, we can classify matter by its state, basically by how closely packed its subcomponents are, and whether they are distributed widely, whether they are moving but closely packed, and whether they're in a rigid, closely packed state. So probably one of the easiest and most pertinent examples of classifying matter by its physical state or physical form is water, right? And so we have a good example here. We have our hipster drinking glass of a mason jar, and within this, of course, we have our ice water. And this particular mason jar is composed of all three of the states of water. And so we have ice cubes, right? These ice cubes, which is a representation of a orderly, closely packed form of these water molecules. We have these wiggling, jiggling, kind of moving around, jostling liquid water molecules. These are all kind of vibrating and moving around quickly through the glass. And then we even have water molecules that are more energetic, and they are water vapor, and they're kind of bouncing around the open headspace of the mason jar. Now in the previous example with water, that was a single substance, and that was identifying it by looking at its different physical states or forms. Often though, of course, we're talking about more than one substance in a container, or more than one substance that we're looking at. A great example might be this cup of tea, the bowl of chocolate pudding, and this mineral. Maybe it's feldspar, it's maybe a quartzite of some kind. And so each one of these is actually composed of more than one substance. And so when we're classifying matter, another way that we can look at this is simply how homogeneous or heterogeneous the material is. So that is to say, how evenly distributed the molecules are between each other, and how undistributed they are. And so we might look at something like this cup of tea. In this cup of tea, we have lots of different molecules. We have tannins, We have flavoring molecules that have been soaked up by the tea leaves, but they're pretty evenly distributed throughout the water mixture, and so we typically describe this as being homogeneous. When we go all the way over here to this rock, right, this quartz rock, we can see that there are actually small inclusions right here and there, and so we actually have a fairly broken up, unmixed piece of matter, and so we're going to say this is heterogeneous. And of course, we actually have lots of things in between, and chemists and other scientists like to think and talk about these materials as well. And so this is semi-mixed right here, this bowl of pudding, and so we actually might call this a colloid, which is kind of a fancy word for what basically pudding is. So here's a nice flow chart that kind of describes what we've been talking about, in that we have matter, anything that we can feel, see, touch, hear, smell, and it's interacting with us. And this matter, of course, we can think about it as whether it's having variable composition, so whether they're pure substances or whether they have multiple substances, a mixture of substances. And if they are a mixture of substances, which is the more common thing for us to encounter in the real world, we have to ask ourselves, whether there's heterogeneous or homogeneous, like this wet sand, which is very heterogeneous, or this tea, which has caffeine molecules, which are evenly distributed in the water. But chemists like to think about classifying matter in a different way. There's nothing wrong necessarily with classifying things as physical states, nothing wrong with talking about how homogeneous or pure a substance is, but for chemists, we like to think about what is the smallest component or the smallest piece that makes up the whole. So if you had perhaps some kind of box, some object, and then you were to actually begin breaking it down by simply cutting it into pieces, you can make it smaller and smaller and smaller. And so the chemist might ask the question, if we were to continue this process over and over and over again, you would get really, really, really small objects. And the question might be, how far can you break it down? And if you get down to a really small building block, does that building block tell us something about the object, about classifying that piece of matter? So believe it or not, this idea is not new. Democritus, a philosopher in ancient Greece, came up with much of the ideas of atomic theory, the modern atomic theory, about 2,500 years ago. Democritus was the laughing philosopher. He was a very clever individual. He came up with a lot of interesting thought experiments, and that is to say that he didn't actually experimentally verify any of his claims or any of his postulates, but he had a lot of really good ideas. And one of the ideas was that the universe was not made out of earth, air, fire, and water, as many believed at the time, or didn't this sort of nebulous kind of ethers, as people would say, that in fact the universe was composed of tiny indivisible objects. So that is to say that if you have a piece of clay, and you were to cut this clay in half, and a 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 half, and you were to keep going on, that eventually you would get to a point where it got so small and that this object could not be divided any further. And he called these things atomos, or atomos, and atomos means indivisible. Okay, so fast forward to the 1800s. John Dalton, a school teacher in England, it offers pretty much the first experimental evidence for the theory that Democritus posited in ancient Greece 2,000 some odd years ago. Dalton is an experimentalist, as I said. He looked at gas molecules, and he came up with this idea, which really kind of mirrors what Democritus said, but he really had evidence for it. This was not widely accepted at first, but then took hold, and now actually this is really the foundation of our modern thinking about the composition of matter. And so John Dalton said that all matter, regardless of its physical states, whether it's a solid, liquid, or gas, whether it's homogeneous or heterogeneous, is composed of extremely small particles that are called atoms, right? Atoms of a given element, right? So now we have new vocabulary here, are identical in properties. And so whether or not you have iron from China or iron from England, that the atoms that make up that iron are going to be the same in both places. Atoms of different elements differ in size, mass, and other properties. So basically, what makes iron different than hydrogen, or different than boron, or silicon, is that the actual atoms themselves are different sizes, they're different masses, and they have other properties that are potentially different as well. He came up with two other postulates as well, which the slide's been cut off here, but that atoms of different elements combine in whole number ratios to form chemical compounds. We, of course, were talking about water molecules, and we had kind of a graphical picture right here of a water molecule. And of course, this is going to be our H2O. And so what he's basically saying is that the atoms are the smallest pieces, the smallest building blocks, and as such, that you can't have half of an atom combining to form some compound or some molecule. This is it. So you are going to have, for instance, combinations of whole numbers, such as 2 hydrogens and 1 oxygen making a molecule. You can't have H 1.503 That's not possible. These are the smallest building blocks that are available to us. And then finally, in chemical reactions, the idea of combining multiple molecules together or atoms together, atoms are combined, they're separated, or they're rearranged. And so basically the idea of a chemical reaction is quite simple. It's that we're taking arrangements of atoms, and we're kind of mixing them up, we're rearranging them. Okay, so here is a page that's been published out of John Dalton's book on modern atomic theory, and if you look closely, you can see he's graphically listed some elements along with a corresponding key so you can interpret them. And then he's even gone as far as to show some molecules that he's combined in whole number ratios to form things that maybe he is experimenting with. If you look closely, you can see that we have carbon and oxygen that he's graphically shown there. And if you look right there, there is CO2. It's a gas that he's probably very familiar with, and hopefully that all of us are very familiar with as well. And so it's from this initial discovery, this initial experimentation, that we are able to come up with the idea of modern atomic theory. That is, that all of matter, regardless of its physical state, regardless of how homogeneous it is, all matter is composed of these small building blocks, these indivisible objects that we are going to call atoms.